안녕하세요. Hello everyone. Welcome back to Automatic Control Systems. This week we're going to actually go through review Laplace transform. Last week we discussed on block diagram reduction technique. This week we are going to focus on how do we actually convert the differential equations into transfer functions, or how do we actually model them, or how do we solve them using Laplace transform. This Laplace transform is quite one of the most important subject, because we learn this one in circuit theory, we learn in automatic control, or we are going to use in various other subjects like signal processing or communication systems. Laplace transform is so important for engineering. These students should really focus on the fundamentals of Laplace transform. Laplace transform provides us the opportunity to actually transform continuous time systems into frequency domain. Coming to here, what we saw in the last class, that we can model any application, any dynamics in the form of differential equation. These differential equations, we need to actually solve these equations to actually analyze the system behavior. So Laplace transforms allows us to solve the linear time invariant differential equations with any inputs, arbitrary inputs. The main advantage with Laplace transform is we can easily combine or break down multiple differential equations or coupled differential equations. Use with block diagrams to find the representation for systems that are made of smaller subsystems. So we can actually draw into multiple block diagrams as well. So if you remember the Laplace transform, what we have here is a two-sided Laplace transform. So if you actually try to understand this expression, we have minus infinity to infinity. F of tau is a time domain function. We're going to integrate with e power s tau d tau. So actually the whole time of the signal properties from minus infinity to plus infinity, we're going to collapse all the time information. We're integrating from minus infinity to infinity, collapsing all the time information and expand in the frequency domain. What is time and what is frequency? Both the domains are the same. I mean in the sense they represent the same system. It's something, the properties we observe in time domain may not be seen in frequency domain, or the properties which we can see in frequency domain we not be able to see in time domain. However, both these domains look at the same system or provide information about the same system. So these two domains complement each other. So that's the major advantage. Now coming to here, most of the engineering problems we actually look for t greater than 0, because now when we start any analysis we assume t is equal to 0 and we actually look in the time domain. We don't go into the past, so we don't worry about the past. So engineering systems cannot go into past. So for real systems the analysis is only focused from 0 to infinity. This is what we call the single-sided Laplace transform. So single-sided Laplace transform, we only focus from 0 to infinity f of tau e power minus s t tau. So this is the practical Laplace transform, and this one is the theoretical Laplace transform. Now let us try to see a simple application of Laplace transform for a time domain system. So if you see here, I have a function f of t is equal to a e power alpha t u of t. If you look here, if you apply input to the system, when I treat u of t as the input, I can treat f of t as the input. Now I have a system here a e power alpha t. Sorry, actually here u is not an input, u is what we call step input. So this can be an input to the system, the e, and this can be an output. So we can actually model the signal as also an input. Now coming to here, u of t is the step input. I think most of you are familiar what is a step. Step is the value of the signal is 0 until t equal to 0. For t greater than 0, the value is 1. So it actually value changes at t equal to 0. So this is a step signal. That means for any t, that is t less than 0, the function value is 0. That means this function has no value for t less than 0. That is what we call unit step. Now I want to apply a Laplace transform. If you see what is e power alpha t, e power alpha t is a nice exponential function. If alpha is negative, let's say e power minus t of t, exponentially decreasing function. So e of t, when t equal to 0, value is 1. Let's say this is a step function. When I multiply with e power minus t, I actually get this waveform. Exponential has more application, or a lot of applications in time domain. So a lot of analysis, exponential functions are very common. So we are going to actually focus on this exponential decay. Now we need to apply Laplace transform to get f of is equal to a by s minus alpha. So let's try a simple analysis. So if you start applying the one-sided Laplace transform, f of s equal to 0 to infinity, a e power alpha t e power minus s t dt. So if you look here, this is the function and this is the Laplace transform expression. So we integrate 0 to infinity e power minus s t dt. This is an integral with respect to time. So if you see here, e power alpha t e power minus s t will be e power minus s minus alpha of t. So then when you integrate this function, e power x from 0 to infinity, you will get into this nice form. And then once we have this form, you can apply the limits infinity and 0, and this become, because e power minus infinity is 0, and finally you will have a simple expression, this minus 1 altogether, you will get a by s minus alpha. So if you look at the expression time domain, a e power alpha t transforms when you apply Laplace transform into a by s plus alpha. All the exponential, all this representation is gone. Most important, t, this is a function of time, and here there is no time. The system, once you actually take this t, transform into frequency domain, t is absent. So in frequency domain, you don't have any t. This is just a function of s, where s equal to j omega. Omega is frequency, omega equal to 2 pi f. So this function is a function of frequency. So we have transformed a time domain function into a frequency domain function. Next application, or a simple application of Laplace transform, is a unit step. Unit step is very popular because the unit step has a single value of 1. For t less than 0, its value is 0. So you apply a Laplace transform, 1 into e power minus st dt. This 1, e power minus st, you get 1 by s e power minus st with limits infinity to 0. When you do that, you get 1 by s. So Laplace transform of 1, time domain 1, will be 1 by s in frequency domain. Not only that, suppose I have a time limited signal. For example, I have a signal that is only valid from 0 to 1, and this value is 3. I want to apply Laplace transform to this. So if I want to apply Laplace transform, f of s equal to 0 to 1, 3 e power minus st dt, then I get 3 by minus s, e power minus st, 1, 0. So what do I have? 3 by s, 1 by e, 3 by s, 1 by 1 minus e power minus s. So this is a very simple expression. So you can actually apply Laplace transform for any time domain signals. Now the most important is impulse or pulse. Pulse is so important. This is very important function which you are going to learn, because you're going to have multiple applications of this impulse in many subjects. A special input has a very simple Laplace transform. If you transform an impulse function, you are going to have unit value in the frequency domain. So one of the main properties of the impulse function, it has unit energy, delta of t, and its value is 0, except at t equal to 0. At t equal to 0, you have this value, and later on, all the function value is 0. So I have this kind of value. Now the other property is it has unit energy. Unit energy means the product, the area under this one is equal to 1. That means this width into this height, the area will give you 1. What you see here, if the width is 2a, the height should be 1 by 2a. That means if the impulse, if you're going to reduce the width, the height is going to increase. When width becomes 0, impulse height is infinity. So impulse is a very dangerous signal. Practically, what is impulse? We can see on the road humps. If a car is traveling, you need to have these humps to reduce the speed. This is also kind of impulse function. Now, if you apply Laplace transform, so 0 to infinity, delta t e power minus st dt, delta is only a value at t equal to 0. So t is equal to 0 to 0 plus, delta of the rest 0 value. So when you do that, you get e power minus s0, delta 0 minus to 0. So I get delta of t dt, that is actually equal to 1. Laplace transform of impulse is equal to unity. So we can think of a pulse in this limit in this form. So the property is f of t is equal to, when f of t is delta of t, is Laplace transform is unit 1. Now let's go to some nice properties. There are two important properties. One is scaling, one is linearity. When I say scaling, just multiplication with some real number. Suppose I multiply a function with some 3. So let's say 3f of t. I know the Laplace transform of f of t is f of s. So what is Laplace transform of 3f of t? Simple, 3 into f of t. So scaling in time domain has no problem in frequency domain. You can simply remove a out of the Laplace transform. It has no problem. That is with the scaling. The second one, linearity. Linearity is when I add two functions in time domain. For example, I have Laplace transform of this one is f of s. I have the Laplace transform of this one is g of s. But I apply Laplace transform of f of t plus g of t. If I do together, I get Laplace transform of f of t plus Laplace transform of g of t. That means even though the time domain signals are added together, you can apply Laplace transform individually to the two functions. So these are two nice important properties. What you can see here, that you can easily test these properties. So if Laplace transform of a into f of t, if you see here, a can be taken outside here. So the system becomes a simple Laplace transform. Even if you have summation of these two signal, Laplace transform of f of t plus g of t, you can write 0 to infinity f of t plus g of t power minus st. So scaling and linearity are quite nice and simple properties for Laplace transform. So here you have a into f of t, I get a into f of s, and if you have f1 of t plus f2 of t, you get f1 of s plus f2 of s, the two properties. Now let us see the Laplace transform of some complex functions. Laplace transform of sine t and cos t can be easily obtained, and it's very popular. I believe you already have learned earlier. So if you want to find the Laplace transform of sine t and cosine t, we see that in Laplace transform we always have exponential term. So if you are able to represent sine and cosine in Euler's forms, the analysis becomes simple. So I'm going to break the sine and cosine into Euler's form. The sine Euler's form is sin omega t is 1 by 2j e power j omega t minus e power minus j omega t. Cos omega t is 1 by 2 e power j omega t plus e power minus j omega t. So you can apply Laplace transform to exponential function. So we saw that in the previous property, Laplace transform of a exponential function will be a by s minus a. So we're going to use the same property, and we can actually observe that e power j omega t is 1 by s minus j omega, e power minus j omega t is 1 by s plus j omega. And then if you mathematically solve, you get Laplace transform of sine is omega by s square plus omega square. And in the similarly, Laplace transform of cos omega t is s by s square plus omega square. This way you can actually solve the Laplace transform of sine. You have to remember these two because these two comes very frequently in many problems and also in the exam. So we have to remember these basic expressions. Now let's go to the other properties. The other two properties we have are the time shift and the frequency domain. So what is time shift? Suppose I know the Laplace transform of f of t, I have the Laplace transform of f of s. Now then, if I time delay the signal, like f of t minus 2, you know the time delay, if you shift the function by a few seconds to the positive axis or to the negative side, the properties change. This is what called time shift. If you shift a function in time domain, what happens is this shift, where t is a number, it can be 2 seconds or 3 seconds, it will become e power minus st naught into f of s. So if you shift a function in time domain, it will affect the signal in frequency domain. That is what you see, that e power minus st naught. Depending on this t naught, you get e power minus st naught. So that is with time shift. Now, what happens with frequency shift? Suppose I multiply e power minus s0t in frequency in the time domain, I have the signal. So if we have this kind of signal in time domain, so what happens is this can actually affect the system in frequency domain. So if you see here, e power minus s0t, if you have in time domain, it actually becomes f of s plus s0. What this is saying is, if you shift if you make a frequency shift in time domain, you're going to see the shift in the Laplace domain as well. So these two, you can easily prove it, but the properties you have to remember. So if you time shift a signal, you're going to get e power minus st in the frequency domain. If you actually have e power minus rho t or e power minus s0t in time domain, it's going to shift the system by s plus alpha. So these two properties are also very important. We're going to see the application in the next slide. Now let us look these two signals, e power minus alpha t, e power minus at cos omega t. So what is sine signal? Let's look at this one. Sine signal, sine 0. So I get a nice waveform. And what is exponential e power minus t? Exponential is a decreasing waveform. And then when you multiply together, what happens? When you multiply a sinusoidal with an exponential function, it actually, the value becomes actually an attenuating or this damped sinusoid. This is what we call damped sinusoid. This is very popular in engineering applications. This pattern is what we see naturally in many places. If I drop a stone in a lake, if you throw a stone into a lake, you see the waveforms are also in this form. Next, if I drop a football on the ground, it bounces with this wave. This is like wave propagation, or any process where the energy decreases with time actually have this phenomenon. So e power minus at sin omega t is a very important function. As I talked to you earlier, suspension system. You know the car wheel suspension. When you hit something, your car vibrates for a few seconds and becomes normal. The car suspension normally is something like this. It has one or two cycles, and then it actually becomes something like that. So this is another aspect of Laplace transform where we can actually see how the time domain signals change. Now if you are trying to apply our property, Laplace transform of e power minus t cos omega t. This to me looks like a frequency shift, right? So now applying this one is a bit complex. So let's see in a different way. What is Laplace transform of cos omega t? Laplace transform of cos omega t is s by s square plus omega square. Then if you do that, then what is Laplace transform of e power minus at cos omega t. This is like a frequency shift. So take the Laplace transform of this one and then substitute s equal to s plus a. If you remember the previous property, this is exactly. If there is any frequency shift, then you have to replace s with s plus s dot. So exactly we are doing. This is the Laplace transform of L cos omega t. Substitute s equal to s plus a. Substitute s equal to s plus a, you get s plus a by s plus a whole square omega square. Now this is the Laplace transform of L e power minus at cos omega t. So this actually gives you simple application of Laplace transform for complex function. If a complex function has an exponential frequency shift or a time shift, you can easily change the Laplace transform. You don't need to solve again the Laplace transform. The same way for Laplace transform e power minus at sin omega t, omega by s square plus omega square, you get s equal to s plus a. So omega by s plus a whole square omega square. So by substituting s equal to s plus a, I get omega by s plus a whole square plus omega square. Now I have e power minus at sin omega t, we have omega by s plus a whole square omega square. For e power minus at cos omega t, I have s plus a by s plus a whole square plus omega square. It's important to remember this function and then understand that when you have e power minus at, you have this form. Let's, for example, I want to find e power minus 2t sin t. So what is Laplace transform of e power minus sin t? Sin t will be, Laplace transform will be s by, omega by, so no, this is not omega. So if you have here 1, t is 1, omega equal to 1. So what we have here is 1 by, what I have here is 1 by s square plus 1, replace s with s plus 2. So replace s with s plus 2. So when I replace s with s plus 2, I get 1 by s plus 2 whole square plus 1. So for any function, you can directly write the Laplace transform of any function with a complex, with an exponential decay or this kind of exponential functions. So this is a very simple way of expanding the Laplace transform. Let's go into the other important properties, what we call integration and differentiation. So if you are looking at integration, it's very simple. When you apply Laplace transform integral signal, you just get 1 by s into Laplace transform of the original function. So if I am having a double integration, I'll get 1 by s square. Triple integration, I get 1 by s cube. Integration is very simple. Now coming to differentiation. If I have a differentiation, Laplace transform of d by dt f of t, I get s into L of f of t minus f of 0 minus. So differential converts into multiplication or a simple s multiplication in frequency domain. And however, you need to also be careful with the initial condition, because when you solve any differential equation, we need to take care of the initial condition. So this you can easily prove with uv different integration by parts. You can take u is equal to dv equal to and then simply prove that. So by using that simple expansion for f of t, you can actually prove this is the case for Laplace transform of differential of function. So integration and differential, you will actually have in this form. Differential of f of t, you get s into f of s minus f of 0. Integral, you can actually show f of s by 1 by s, but this integration is 1 by f of s is the most easiest form of representation. Now simple examples of Laplace transform. If you apply Laplace transform of time, that is integral of, so time, if you integrate u of t is this function, if you integrate, you're going to get this kind of function. So if this is the unit step, when you do integration, you're going to get this kind of ramp. So time can be written as integral of u of t dt. So if you actually apply Laplace transform, integral is 1 by s, Laplace transform of u of t is 1 by s. So you get 1 by s square. So simple application. The same way, Laplace transform of t e power minus at, you can see this because of e power at, Laplace transform of t is 1 by s square. Take from here and replace s with s plus a. So you have 1 by s plus a whole square. These are also very important properties and examples. And next, derivation of a step. When you derivate a step, you're going to get impulse function. Derivative of this one, you get simple impulse function. So derivative of step is impulse, so you can use an impulse function and actually use that, so we can get a actually value of 1. That's for derivative of step. Derivative of sine is cosine, so you can try that in Laplace transform. Laplace transform of derivative of sine t by dt, you can get derivative is s. Laplace transform of sine t is 1 by s square plus 1 minus 0, so you get s by s square plus 1. This 0 because initial value of the function is 0 because of the initial value. So that gives us simple expressions for time, t into e power minus at, differential of a unit step, and differential of a sine t. So if you see time, you get 1 by s square, t e power minus at is 1 by s plus a whole square. Differential of u of t is 1, d by dt of sine t is s by s square plus 1. So the properties are very important here, the properties of Laplace transform. So time differentiation we saw for first order. Suppose you have nth order system. So nth order is s power n f of s minus integral 0 to n minus 1 s power I dn minus 1. So you will have a nice expansion. I'm going to expand and explain you in the later next slides. So how to write simply for various form. Next, the time integration. Integration is easy depending on the number of integrals. Suppose you have 3 integrals, it will be f of s by s cube. N integrals will be f of s by s power n. The next one is complex translation or shifting in the frequency domain. So if the Laplace transform has e power minus at or plus t into multiplication f of t, you get f of s plus a. So this is another nice translation or a frequency shift. So all these properties are very important. So time differentiation, time integration, and complex time. So differentiation is multiplication by s power n. If integration is divided by s power n. If all the initial condition f0, f dash of 0, f double dash of 0, f triple dash of 0 are equal to 0, this can be 0. But it's not common in all the problems that you have initial condition, all the initial conditions 0, but many problems may also have initial condition. So it's very important to go through the system in this manner. Then the real translation, that is the shifting in time domain. You have f of u t minus t of t, you have e power minus s t f of s. Convolution is like multiplication in frequency domain. If you convolute 2 signals in time domain, they become simple multiplication in frequency domain. So convolution is defined as f of 0 to t, f1 of t, f2 of t minus t. If you are not familiar with convolution, don't worry, you can ignore that. But students who already learned convolution or signals and systems, they might be familiar with the convolution. So convolution actually, it doesn't matter which function you are reversing and mapping the whole time, you can have the same. So Laplace transform of any convolution signal. This is not multiplication, this is convolution. Then it's a simple multiplication in frequency domain. Next, the initial value theorem, the last property. What is the function value initially? What is the function value at t equal to 0? That is what called initial value. Initial value is important because systems or functions, initial energy changes everything about the system. So our initial value is very important. And the final value theorem as well. So the final value theorem is what happens to the function when t tends to infinity. When t tends to infinity or when t tends to infinity after a long time, what happens to the system? Is the system being stable or a finite value? We're going to actually see from final value theorem. Final value, if the system is stable, then we can say the final value theorem is equal to 1. This slide, we're going to come back later, so don't worry. So we're going to discuss this one after the Laplace transform is over. I'm going to come back to this slide later. So this is the end of our lecture for this class on Laplace transform. In the next class, we're going to discuss on review of Laplace transform 2. So this will be the end of week 2, part 3. Thank you. Samida.